All right, we'll get started. Welcome back. And last lecture, we briefly discussed the chemical potential. What is an ideal gas mixture? What do we know about ideal gas mixture? And we sort of started talking about the equilibrium constant, right? So as a quick review, in our last lecture, we first used the definition of chemical potential, and then we went over the derivation to study the chemical potential of a pure ideal gas, right? So as a review, the chemical potential of a pure substance, one-phase system, is equal to the molar Gibbs free energy, or GM. And now for isothermal processes, we did a derivation to say, hey, isothermal, so temperature is not changing, my d mu equals to dGm equals to Vm dP. Right, so we went over that discussion and went over the derivation to say like, hey, now we have the change of chemical potentials for an isothermal processes of a pure ideal gas, right? And we went over the derivation of this equation, which is the general equation for pure ideal gas. All right. And then from there, we took one more step further to discuss ideal gas mixtures. So I want to spend a little bit more time looking at ideal gas mixture. So in here, we have our PV equals nRT. So N here is our N total. So the first criteria for the ideal gas mixture is pretty straightforward, saying the mixture also follows the ideal gas equation of state. The second one, I'm going to spend a little bit more time here. What we're doing here is we're saying for an ideal gas mixture that is at equilibrium, you can imagine this special case. Now, in the top chamber, we have an ideal gas mixture at certain temperature and pressure. Now, in here, let's imagine we have like ideal gas A, B, and C, right, in some kind of more fractions mixed together. Now, in the bottom chamber, alternatively, let's say we only have gas A in my bottom chamber, right? But we can set so that the top chamber and the bottom chamber are in material equilibrium with each other. They are separated by a like thermally conducting rigid membrane that allows only gas A to permeate through. Right? But by setting up this equilibrium, we can show that, okay, first of all, the temperature is the same. If we're only focusing on the partial pressure of A, we see that the partial pressure of A in the top, or PA, in my ideal gas mixture equals to chi A times total pressure P. On the bottom, we only have my gas A, right? So my PA now can have a little star on there. So what we're saying here by setting up this equilibrium is that on the top, we're talking about the chemical potential of my mixture, or on the top, we have the chemical potential of my species I will be a function of T, P, like say chi A, chi B, and chi C. Right? Even if we're only looking at A. That's on the top chamber. It's a mixture. So it's a function of pressure, temperature, and the mole fraction of all the components in that mixture. But if we look at the bottom chamber, we only have my species A in my bottom chamber. So this chemical potential is a pure chemical potential. So this little star denotes this is a pure substance. Now in the bottom chamber, we only have one species. So it's a function of temperature and also this chi I, or let's say, let me put it this way, PA star, right? So this PA star denotes for the pressure of my pure substance A. And for this ideal gas mixture, my PA star equals to chi A total number P. And the top one and the bottom one are in equilibrium with each other. So that's why in our next page, we say like, hey, these two are in equilibrium with each other. These two chemical potentials must equal to each other. All right, so that's how we derived our equation on the next page by saying like, hey, for ideal gas mixtures, even if you have different component in there, the chemical potential of my component A in the mixture is equal to the chemical potential of my pure component A as a function of temperature and its partial pressure. All right, so this one, I think I didn't get it like crystal clear in my last lecture, so I want to further illustrate that point here. It's when we're setting up this equilibrium here, that's what we're doing here. We're demonstrating these two chemical potentials are equal to each other. And what else? We also know for these pure species, right? We in our previous section, we derived that for this pure species, we have an expression for this pure species I equals to mu I naught T plus RT ln P over P naught, right? But now my P in this chemical potential is the partial pressure of my species A, B, or C in the ideal gas mixture. And hence we went over to say this is our final fundamental thermodynamic equation of an ideal gas mixture. This is where this equation comes from. Yes?
P naught is just 1 bar.
Yes, P naught is just 1 bar. That's just a standard pressure. Okay. It's just to give us a reference point. Okay, how are we doing? We're doing fine? That's just a quick review in like what we discussed in our last lecture. And now today we'll focus on equilibrium, right? So we went over to discuss like what is chemical potential for ideal gas mixture, how do we define ideal gas mixture, and now we're ready to talk about chemical reaction equilibrium of ideal gases, right? So first step, you mix your chemicals together in a chamber, reactant and product together, and now they'll undergo chemical reactions. And now today we want to go over processes of describing that ideal gas reaction equilibrium. So at the end of our last lecture, went over the review in what is happening at equilibrium, right? So remember, we started by looking at the fundamental information we know, which is the sum of my chemical potential times the Ni, that equals to 0. And for a chemical reaction, the Ni equals to stoichiometric coefficient times the infinitesimal change of the reaction extent C. And replacing this into the Ni, we went over to say like, hey, at reaction equilibrium, we must have the sum of the chemical potential times the stoichiometric coefficient of each substance involved equal to 0. So now we're ready to use this information we have and to write out the definition for chemical equilibrium constant Kp, and then we'll do one example problem together in like how do we use Kp to solve for specific chemistry problems. So first, the definition. Here are all the things we need, right? So a few things. We're gonna use some kind of hypothetical reaction, AA plus BB goes to CC plus DD, for some kind of hypothetical ideal gas reaction. So an ideal gas reaction basically tells me my A, B, C, and D, they're all ideal gases. And at equilibrium, we just say we know my sum of my stoichiometric coefficient times the chemical potential must equal to 0. And also we have our fundamental thermodynamic equations for my ideal gas mixtures. So I'm gonna do this on the board because I want to keep this information here so you can look at it. If you're watching the recording, please refer to my annotated notes and look at what's on the board basically. So what we're gonna do at first, right? So first of all, we're gonna write out what that equation is, or translate that chemical potential and stoichiometric coefficient sum. So from here, we're rewriting my mu I summation equals to 0. And since we have AA plus BB goes to CC plus DB, right? So my stoichiometric coefficient here is negative A, negative B, C, and D. So negative for reactant, positive for product. So this equation effectively becomes my C mu C plus D mu D minus A mu A minus B mu B, and that equals to 0. All right, and I hope people in the back can see my handwriting. Okay. And then the equation we want to use is my fundamental equation for any chemical species mu I, that equals to the standard mu I at certain temperature T plus RT ln PI over P naught. Right, so basically we're going to write this equation, which is the chemical potential for our mu C, mu D, mu A, and mu B. So just plug in this quantity into all the chemical potential terms in here. And this becomes a little bit tedious, but this is what we have. Mu C naught plus RT ln PC over P naught plus D times mu D naught plus RT ln PD over P naught minus A mu A naught plus RT ln PDA over P naught minus B mu B naught plus RT ln PB over P naught. And that sum equals to 0. Just a little bit tedious, I mean nothing fancy, we're just plugging the number. Why are they all fragments? I'm just trying to find a good chalk, sorry. Okay. And then we're just gonna move things a little bit around because I want to keep my standard state together and my RT line term all at the same place. So basically I'm moving all the chemical shift, all these standard chemical shifts, we're gonna leave them on the left and move all the logarithm term to the right. And that becomes C mu C naught plus D mu D naught minus A mu A naught minus B mu B naught, and that equals to negative RT. So RT is just a constant, we can take that out. C ln PC over P naught plus D ln PD over P naught minus A ln PA over P naught minus B ln PB over P naught. Right. Nothing fancy, just moving terms around. And now we're ready to think about it, right? We have this long equation. What exactly does all these terms mean? So first of all, if we focus on the left side, so what are these terms? Now this mu C naught, like we're talking about the standard chemical potential of a pure substance, A, B, C, or D, right? So for pure substance, like A, B, C, and D, we know that, say, for example, mu I naught equals to the molar gives free energy, molar standard gives free energy of that chemical species. Right, so we can rewrite this equation into, say, C G naught N at certain temperature C plus D times G naught N TC and minus A GN naught certain temperature, this should be A. A minus B times Gm naught, certain temperature and compound B. Right, or the other way to put it, what are we putting here? This summation is the same to say this is the sum of all species involved in my chemical reaction with their stoichiometric coefficients times the molar, the standard molar Gibbs free energy are at certain temperature for chemical species I. All right, so my left-hand side is effectively this term. Or what is this term? This is just the Gibbs free energy of the reaction. Or this one will be my delta G naught at certain temperature. Or that's my standard Gibbs free energy change of a certain reaction at given temperature T. And remember in our last chapter, we went over how to use the thermodynamic table to come up with this value, right? So just to make a link, what is on my left-hand side? All right. What about the right-hand side? And now we're focusing on the right-hand side with all the logarithm terms. So in here, one of the things I want to, again, refresh your memory is we know that for logarithm functions, right? So if you write some kind of, well, let's say, some kind of x outside like ln y, that's effectively equals to ln y to the x, right? And for ln x plus ln y, that basically gives you ln xy. Or ln x minus ln y, that gives you ln x divided by y. Just a little bit refreshment on logarithm mathematics. So with that in hand, what's on the right-hand side if we put everything inside a logarithm function? This right-hand side thus becomes negative RT, and inside there, we have my PC over P naught to the power of coefficient C, and then PD over P naught to the power of coefficient D. And on the bottom, since we have negative in front of A and B, we have PC over P naught, or PA over P naught to the power of A, PB over P naught to the power of B. So that's our right-hand side. All right. So now we're ready to say, hey, let's just define whatever inside that logarithm to be our equilibrium constant. Or we define whatever inside this logarithm to be our Kp. And that's a big Kp called standard equilibrium constant. Right. So on the board, we're using a special example, which is like AA plus BB goes to CC plus DD. Now, as a general format for what we just derived, if we're looking at this typical reaction, right, just looking at any kind of reaction, goes to stoichiometric coefficient times the reaction species. So we're back to the slides now. And what we just find out is, first of all, we have my delta GT, that's left-hand side, equals to negative RT ln Kp naught, right? So that's our equilibrium constant. So we have our delta GT naught equals to negative RT ln Kp. Right, and how is Kp defined? So in here, my standard equilibrium constant, Kp, is defined as a series of products. So this big pi stands for product. Again, it's just a new mathematical symbol that looks horrible, but like if you think about big pi from like I equals to 1 all the way to n of AI. This basically tells you we're doing the product of AI of A1, A2, A3 all the way to AN. Right, it's just a series of products. So in here, for our equilibrium constant, we're saying it's a series of products of my partial pressure at equilibrium over our standard pressure, which is 1 bar P naught, to the power of its stoichiometric coefficient. Right, so positive for our product, negative for our reactant. All right. Alternatively, people also write the top equation. It's the same idea. If we want to express Kp as a function of delta G, we have my Kp naught equals to the exponential of negative delta G naught over RT. Right? Just natural log and exponential function. They're the reverse of each other. All right, and for ideal gas reactions, we will be using these relations together to solve for like composition of the reaction mixture at equilibrium or vice versa. All right, so this first part, we spent about 15 minutes to give a solid definition in what is equilibrium constant using a sample reaction. And with that in hand, we further generalize that definition into any kind of reaction has a general format of 0 goes to stoichiometric coefficient times the reactant or product. And we went over to this general expression in like say, hey, delta GT, the standard Gibbs free energy of the reaction equals to negative RT ln Kp. And my Kp is defined as a product of my partial pressure over P naught to the power of its stoichiometric coefficient. Right. And now we're ready to use whatever we just defined to solve some problem. So do this example problem together. We'll read the question together first. I'll write down information that you should be putting down when you're reading the question and show like how to set up the problem. And then we'll do the problem together on the board. So let's read the question. It says like 0.15 more of oxygen 2 gas is placed in an empty container. And we allow the reaction to take place until a reaction equilibrium is established at 4,000 K. One find that the pressure is 2.175 atm at equilibrium, and asks for the standard equilibrium constant and delta G for this reaction at 4,000 K. So a few things we can say. First of all, we see like assume ideal gases. So instantaneously we can write out PV equals to nRT. Now this N is N total RT, right? There's a reaction going on. Even if we only put in oxygen O2 gas, the decomposition of O2 to form elemental oxygen may be taking place. So at equilibrium, we're talking about an equilibrium between my reactant and product at equilibrium. So since we're talking about chemical equilibrium, because the question reads that equilibrium is established at 4,000 K, right? So in this information, we can write down what we just defined, delta GT equals to negative RT ln Kp naught, right? The question asks us to solve for both Kp naught and delta G naught, so obviously we need this equation to solve one from the other. And note that in this case, my temperature equals to 4,000 Kelvin, which is at which the equilibrium is established, right? So this is why we cannot directly use the appendix table to solve for delta G, because appendix table doesn't give me delta G naught for temperature at 4,000 K. All right. What else do we know? We also have the definition of my equilibrium constant. So we have our Kp naught equals to the product of my Pi, my partial pressure over P naught and the stoichiometric coefficient. Right, so this is actually going backward. What the question is asking us is to find out what is my Kp and delta G naught. So looking at what we have a relationship between delta G naught and Kp naught, right? I don't have a way to solve for delta G naught, but do I have a way to solve for Kp naught? I may, right? So my Kp naught is the product of my partial pressure of my reactant and product timed together to the power of its stoichiometric coefficient. Right, so what is my partial pressure? Now the question becomes, how do I solve the partial pressure? And that comes to I know my initial number of mole of my reactant. I know the total number of mole of my reactant and product summed together. I also have the relationship, the stoichiometric relationship between my reactant and product. So that means to solve for my Pi equilibrium, we can use my reaction here to solve for my extent of reaction C and use it to calculate my partial pressure, right? So that's the general logic behind hey, when you see a problem, how to use something like we learned in class, how to set up that problem so you're on the right track. So we can work on this together. And again, if you're watching the recording, you can refer to my annotated notes to see how we solve the problem. Okay. Right, so first of all, what do we know, right? We have an idea about the first step is to solve my total number of moles, or let's say to solve for my partial pressure of my oxygen and elemental oxygen, right? So oxygen O2 and elemental oxygen. So what do we know here? We know the total number of mole at equilibrium. We know my total number of mole equals to my number of mole of oxygen at equilibrium plus NO at equilibrium, and that equals to PV over RT. Right, so that's what the question is giving us in conditions at equilibrium. That's 4,000 K, 2.175 ATM, and we have 22.8 liters of my container. So I have all three pieces of information I need. So plug in those numbers. Well, P is 2.175 ATM times 32.80 liter. R is 0.0821 ATM per liter per mole per Kelvin, and 4,000 Kelvin. If you're using different units, translate to joule or something, that's the same, just transferring up units. So we do that calculation, we end up getting my total number of mole equals to 0.2172 mole. All right. And the next step is to use the stoichiometric relations to solve for the actual number of mole of O2 and elemental oxygen at equilibrium. So what do we know? We know that at initial state, my Ni, which I now stand for initial, of my oxygen equals to 0.1500 mole. And my initial state of elemental oxygen, that's 0.000 mole. So there's no elemental oxygen at my initial state. And we have our change. Right, so given this reaction here, we have like O2 decompose into two oxygens. So the stoichiometric coefficient in front of my oxygen is -1. So I put -C here. And for my elemental oxygen, that's going to be 2C. So the final, or equilibrium, what we have point, so NO2 at equilibrium equals to 0.1500 minus C. And my NO equilibrium, that equals to 2C. And what else do we know? We know that these adds up to be my point. So these two add up to be my N total. Right, so what we end up having is 0.1500 plus C equals to 0.2172. So we can solve our extent of reaction to be equals to 0.0627 more. Right, so how does that contribute to calculate our partial pressure? So my partial pressure here in ideal gas mixture, that equals to my mole fraction times the total pressure. Right, so do I know what my mole fractions are? And yes, we do, right? Because with our solved extent of reaction, we can solve for our number of moles of O2, our number of moles of oxygen, and thus we can solve for our partial pressure here. So I'm not going to spend too much time plugging numbers. I can just tell you we can solve for my PiO2 at equilibrium equals to chi O2 at equilibrium times the total pressure. Now my chi O2 at equilibrium is this one. So 0.15 minus C over the total, which is 0.2172, and times my total pressure, which is 2.175 ATM. Or you can translate that into bar. And that gives you some number, like say in this case 0.8402 bar. So that's our first step, right? So this part is nothing fancy. We're just using lots of new symbols, but they're just your general chemistry calculation, right? What is going on? How many number of moles of my reactant has been transferred into product? What's the extent of reaction? How to use that mole fraction to calculate the partial pressure of the reactant and product involved in this chemical reaction. All right. And well, next, the same thing will apply to calculate the partial pressure of your elemental oxygen. And that's, I'll just give you the number so you can check your calculation later. But effectively, yes, we can calculate the partial pressure of my reactant and product by calculating the extent of the reaction. And then it becomes very straightforward, right? So we have our partial pressure. We have our definition of the equilibrium constant. So we're ready to put my Kp naught equals to the product. Right, so in this case, we have, for my oxygen, we have -1 in front, so that's my 0.8402 over 1 bar. So that's why I translate it into bar when I write the partial pressure. And to the -1, right, so that's my stoichiometric coefficient of oxygen. And times the product, which is 1.364. over 1 bar, and to the power of 2. And that's my stoichiometric coefficient of my elementary oxygen, O. So plug in the number, you get that to be 2.214. Right. And delta G naught just becomes very straightforward. We then have delta G naught at this 4,000 Kelvin. That equals to negative RT ln Kp naught, and that gives you negative 26.4 kilojoule per mole. Or it tells me this is a spontaneous reaction that is going downhill and gives free energy, or a spontaneous forward reaction. All right, so this one is a demonstration in how, now we have defined our equilibrium constant. How do I use the terms we defined to solve something that's of real like chemical interest? All right, and then moving forward, we went over our definition of our equilibrium constant based on partial pressure, right? You can rewrite my partial pressure equals to the mole fraction times the total pressure, or you can write that as Ni RTB. There are different versions of the equilibrium constant. So instead of using the partial pressure, we might also give you like molar concentration. Like for example, molar concentration is defined as Ci equals to Ni over V, right? So my Kp, if you think about it, my equilibrium constant, that P refer to pressure, equals to the product of my partial pressure of each species over P naught to its stoichiometric coefficient. And then we also have Pi equals to Ci RT, so that comes from like this one, times RT gives you Pi, right? So your mole fraction times RT gives you Pi. And you can rewrite that as the molar concentration version of the equilibrium constant to be the product of my Ci equilibrium divided by C naught at mu I. Right, so this mu I here, that's also my stoichiometric coefficient. It just depends on how my standard state is being defined. Now, in previous case, my P naught equals to 1 bar. So my standard molar concentration is typically 1 mole per liter. Just different versions. This is just conversion of unit, nothing fancy. Okay, and one more step. Now we have a way to express my Gibbs free energy and equilibrium constant for isothermal processes, right? So all in our previous derivation, we're always talking about isothermal processes where temperature is not changing. So how does equilibrium constant change with respect to temperature? So this part comes to the derivation of the Van 't Hoff equation. All right, so the Van 't Hoff equation, or the other way to put it, is we're trying to derive how does my equilibrium constant change with respect to temperature. That's what this temperature dependence means. So you see, temperature dependence asks you how does my property change with respect to temperature. Volume dependence means how does my property change with respect to volume change, right? So temperature dependence is asking us to find what does the ln K, or my equilibrium constant, how does it change with respect to temperature. So we're trying to solve for an expression here and find out what that relationship is. So a few things we will be using. We'll first use this equation, which again, that's our delta G equals to negative RT ln K. And at the same time, I'll also use my Gibbs equations and also calculus to try to prove or to derive an equation to find out how does my equilibrium constant change with respect to temperature. So again, I'll leave this information here on the board, on my iPad, and I'll do it on the board. if you're watching the recording, you'll have all those derivations in my annotated lecture notes. All right. So the question asks us to find out how does my ln K change with respect to temperature, right? So starting from my ln Kp naught equals to negative delta G naught over RT. So obviously the first thing is to take differential of temperature on both ends. So that becomes the differential of d ln Kp over dt equals to d over dt, and inside we have negative 1 over RT times delta G naught. Right, so it's always safe to say on both ends, I'm taking that equation with respect to dt. Now on the left-hand side, we already have what we want. So I'm just going to focus on the right-hand side and see how can we further simplify this equation here to give it a little bit more chemical meaning. Now inside here, what do we have? We're looking for a differential over temperature, right? But we have delta G naught as a function of temperature. We also have temperature here. So it's hard to solve it directly. But using calculus, which is, well, dxy equals to x dy plus y dx, right? So in here, my x will be my negative 1 over RT, my y will be my delta G naught. So we can rewrite this expression here into, well, d over dt. On the front, we have y, well, let me put y dx first. So delta G naught times that of 1 over RT plus 1 over negative 1 over RT d dt of delta G naught. Right, so just using calculus, very straightforward. Now this one we can solve. It's just like differential of d over dt of negative 1 over t. So the first part becomes our delta G naught over RT squared. And my last second part becomes negative 1 over RT d delta G naught over dt. All right. And for this term here, for this delta G, d delta G naught, we need to take one more thing, right? What is my delta G naught here? So the delta G naught in here, again, whenever we're doing this derivation, it's always good to ask yourself, what am I writing down? So in this expression, this delta G naught is a standard Gibbs free energy of an ideal gas reaction. Or my delta G naught equals to the sum of my all the reactant, the stoichiometric coefficient, times the molar Gibbs free energy of each species involved in a chemical reaction. All right. Or the other way to put it is if we put my differential of delta G naught over dt, we're taking the differential of this entire sum of the stoichiometric coefficient times the molar Gibbs free energy of each species. Now in here, my stoichiometric coefficient, that's irrelevant, right? That's not dependent on temperature, so I can take that out. That becomes the sum of my stoichiometric coefficient times d gt mi as a function well, GMI over dt. With me so far? So what do we know about the differential of my molar Gibbs free energy over temperature? So that goes back to my Maxwell relationship. So if you have our equation sheet with you, or I can pull it out for you, we're looking at how does my Gibbs free energy, molar Gibbs free energy change with respect to temperature at a given pressure, right? This little knot tell me my pressure is at 1 bar or at constant pressure. Now, in my thermodynamic relations, right, that's why we care about thermodynamic relations, we see that gives us my delta S, or negative S. Or the relation we're trying to use here is the partial differential of Gm over T at constant P equals to negative molar entropy. All right, so now we're ready to say, okay, so inside here, these are my molar entropy, or these are my standard molar entropy of my species I. So we can further simplify this sum to be the stoichiometric coefficient times the molar entropy, the standard molar entropy of species I. Or this summation thus becomes my, and there's a negative delta S naught of the reaction. All right, how are we doing here? So it's like using something we derived before. So if this kind of derivation showed up, I'll give you a hint to say like, hey, you might want to use Maxwell relations when doing this derivation. But we are using something we learned before. All right, so what is on our left-hand side? So on our left-hand side, we have what we want, right? So going back to our original equation. So on the left-hand side, we have our, let me make some space here. We have our D line Kp naught over dt. That's on the left. And on the right-hand side, we have my negative 1 over RT and times my negative delta S. That's this part, right? We find out this differential of d delta G over dt equals to my negative delta S. And this term becomes negative delta S. So that's where this comes from. And plus the first term, which is my delta G naught over RT squared. And now we're ready to simplify our terms. So we can put my RT squared outside the bracket. So that becomes 1 over RT squared. And inside we have negative G naught, delta G naught plus T, delta S naught. So my negative and negative cancel out. If I take my RT squared, yes?
Could you put the computer down?
It says please do not turn screen. I'm gonna do it nevertheless. So now the minus and minus cancel out, right? And then inside the bracket we have my delta G naught plus T delta S times 1 over RT squared. And what is this one? And my delta G naught plus T delta S. Right, we have G equals to H minus T delta S. For a set temperature, for a certain temperature here. Or the other way to put it is that our final version of our Van 't Hoff's equation thus becomes my d ln k naught over dt equals to delta H naught over RT squared. All right, and the power of the Van 't Hoff equation, if we think about it, now we have a differential equation, right? We know that how does my equilibrium constant change with respect to temperature. Now, equilibrium constant is something we can experimentally measure by knowing the composition of my reaction mixture at equilibrium. So by measuring the equilibrium constant at different temperature, we have a way to calculate delta H naught of the reaction. All right, or the other way to put it, the actual plot, which is more straightforward, is that if we are using the differential of 1 over t equals to negative t squared dt, or my dt equals to d 1 over t over negative t squared. So what we're saying is we can further simplify the Van 't Hoff equation to say, like, if we plot ln Kp with respect to 1 over t, we're getting negative delta H naught over R. Or it's a linear relationship if we're plotting the ln Kp over 1 over t. So like in all previous cases, right, we always give you the definition of a term, went over the derivation of a general equation, and in our next lecture, we'll look at examples in how do we use the Van 't Hoff equation in a specific application. Like, we're gonna use this example as a test case to show, like, okay, how do we use this plot that is experimentally obtained to get delta H naught? And to think about the more general question, how does my delta G, delta H, delta S, and my logarithm of equilibrium constant change with respect to temperature for this kind of reaction? So we'll pick up next lecture. So we basically done introducing all the terms we need. So next lecture, we'll all be doing problems together. So problem solving and application of the things we derived. I know I'm behind. We'll see how far we go, and whatever we covered until next Wednesday, that's the last coverage for your final exam. We'll see how we go. All right, that's all from me today.